So I'm Stefan. I'm going to talk about the novel imitation learning approach that's related to no-regret online learning, and that's joint work with my advisor, Drew Bagnell, and Jeff Gordon. Okay, so in imitation learning, what we're basically trying to do is make a robot learn how to perform some task by watching an expert doing it. So you might have a mobile robot like this, and we'd like it to be able to traverse some terrain and reach some goal location. So we might have an expert who can teleoperate the robot around and show how to navigate across the terrain efficiently. And so what we'd like to be able to do is apply some kind of machine learning algorithm that can take these expert demonstrations as input and output a policy that we can just run on the robot, and the robot will be able to achieve that task by itself. So there's been many successful applications of imitation learning in recent years. These are some examples. And so the sort of main advantage of imitation learning over other more traditional control methods is here you don't have to provide any sort of complete or accurate model of the world, and you don't have to be able to end-tune all the parameters of your cost function so that you get the proper behavior out of a planning algorithm, for instance. All you need to be able to do is demonstrate how to perform the task. And that's often much easier for humans to do, especially on those complex robotic systems. So now let's look at a particular example and see how we can learn a policy for our robot from these expert demonstrations. So let's look at the following scenario. Let's say I have a car and I want it to be able to drive itself on the road. And my car has a camera sensor, so it can see what's in front of the vehicle. And so what I'd like to do is learn some policy that can take these input camera images and predict what kind of steering it should do in the environment to stay near the center of the road. There's sort of like a very trivial and simple training procedure you could think of to do this. And what you could do is just have the human drive the car around the environment. And as the human is driving, you record these images that are being seen by the camera, and also the steering being executed by the expert. And so what you do is you build this big data set of input images that you see with their corresponding associated steering. And so now you could just treat that as a standard supervised learning problem. So apply your favorite classification or regression algorithm, and you'll get some policy out of it that can take any input image and predict some kind of steering angle. So this sounds like a reasonable approach, right? Well, turns out that if you do that in practice, you'll often get a very bad performance at the task. So I'm going to show you a video that illustrates what goes wrong with this approach. So here what you're seeing is me playing this racing game, collecting training data to learn a controller that can steer the cart in this game. What you can see is when I'm driving mostly near the center of the road. So all the examples that the learning algorithm sees is what to do near the center of the road. But now when you run the learn policy, what happens is it's not perfect. It still makes some mistakes. So what happens is it ends up in those new situations near the side of the road where it doesn't have any training data. So it doesn't know how to recover when it's in those bad situations. And so it just makes more mistakes and falls off the road. So what we can see in this video is there's this key distinction between supervised learning and imitation learning. In supervised learning, we assume that our test data comes IID from the same distribution as our training data, but that's not the case here. Here what happens is the predictions that you do at test time changes the future observations or states that you're going to see in the future and be tested at. So the test data is not IID and depends on the actual policy that you run at test time. So because of this, you can actually show that in theory, this supervised learning approach has pretty poor performance guarantees. So in particular, if you learn some policy that makes a mistake with some small probability epsilon under the states that are visited by the expert during training, and you run that policy for t time steps at execution time, then under its own trajectories, it could be making as much as t squared epsilon mistakes in expectation. So that's pretty bad because if you compare this to the standard IID setting, you expect to make t epsilon mistakes if you have to classify t new test examples. And that's also both an upper bound and a lower bound because we can construct examples where this holds with equality. So sort of natural question you can ask is, well, can we develop some new learning algorithms that can provide better guarantees than this in this imitation learning setting? And it turns out we can if we allow the learning algorithm to sort of do its own actions during training and collect more data about the expert behavior, about what to do after you make those mistakes in the environment. So that's the kind of strategy that will be employed by the learning approaches I'm going to show you. And the way we're going to analyze these approaches is doing this kind of reduction-based analysis. So the idea of a reduction is you can take some hard learning problem and you reduce it to solving a sequence of simpler or easier related problems. So an example that you might be familiar with is a reduction of multi-class classification to binary classification. So in that case, what you do is you solve these sequence of binary classification tasks from which you can construct a multi-class classifier. And then what you can also do is bound the performance on the original multi-class classification problem as a function of how well you can do at those binary classification tasks. So we'll do a similar idea here. Well, we'll reduce our hard imitation learning problem to solving a sequence of classification problems. And we'll be able to bound how well we can do at the original imitation learning problem as a function of how well we can do at at the sequence of classification problems. So now I'm going to briefly mention two previous approaches we've proposed here last year that can guarantee better performance guarantees than this supervised learning approach I showed you earlier. But so these approaches are nice in theory, but they have some drawbacks in practice that our new approach will be able to deal with. So first one is called forward training. And the idea here is instead of learning a single fixed policy, you're going to learn a sequence of policies. So you train a non-stationary policy. And the way you train that non-stationary policy is you learn one policy for each step in sequence by starting at learning the first policy for the first step. So what you do is you just collect data of the first states you see in the environment, what the expert does at those states, and you train the first policy on that data. And then to train your second policy, now what you do is you simulate the first policy you learned for the first step to see what kind of states you end up at the second step. And then you ask the expert what to do there, and you train your second policy on that data. And you just keep going on like this. So train one policy per iteration of the algorithm for one step. And so what you can show about this approach is now when you're going to run that sequence of policies that you've learned at test time, your expected number of mistakes is linear in t and scales with epsilon, the average error rate of the classifiers that you've learned. So that's really nice because now we achieve the same bound that we could guarantee in the IID setting, even though this is like a non-IID setting. So that's pretty good, but the sort of drawback of this approach is it's impractical when t is large or unknown. So for many tasks, we might not know in advance how long we're going to have to run our policy, so we don't know how many policies we have to learn. Or if I have to run my policy for 1 million iterations, then I have to run this algorithm for 1 million iterations and learn 1 million policies just to get my complete policy to run at test time. So often we can't do it this approach. So sort of address this problem, we've also proposed another approach last year, which was called SMILE, and that's a similar approach to CERN or conservative policy iteration, if you're familiar with that. The idea here is we train a stationary stochastic policy over several iterations by making small changes to the policy at each iteration. And the way this approach works is you essentially use your current policy so at each iteration what you do is you use your current policy to collect more data about the expert in those states that you encounter by running that current policy. And then you find the best policy at mimicking the expert in that data. And then you add some small probability of running that new policy to update your current policy. And you just do that over many iterations. If you do that for long enough and make that parameter alpha small enough, then you can also guarantee good performance guarantees with this approach. But what's bad about this is you get a stochastic policy out of it. And often when you want to run this on a robot in the real world, you don't want to run a stochastic policy. You don't want to start picking some bad actions some of the time. So that's what our new algorithm will allow us to do. We'll be able to learn a deterministic stationary policy. That's much better in practice. So now I'm going to present our new approach, which is called DAGGER for dataset aggregation. And it's very simple to implement. and we'll be able to provide the sort of same guarantees as in the ID setting. So here's how it works. At the first iteration, you do basically the same thing as the supervised learning approach I showed you earlier. So you just have the expert drive the car in the environment, collect data while the expert is driving, and then you'll get a first data set that you train your first policy on. But now what you do is you iterate. So at the second iteration, you're going to run that first policy that you learn. So now it's like the computer is driving the car, and as the computer is driving the car, you still ask the expert what it would do in those states or observations that you see. So it's like the computer is driving and the expert says, hey, turn more to the right. No, turn more to the right. No, really, you should really turn to the right. And so you get this new data set of examples. And now what you do is you aggregate that new data set with your previous data set that you collected for the first iteration. And you train your next policy on that giant data set of all the data you've collected so far. And so the algorithm just keeps going on like this. So the next iteration, you use your current policy, run it in the environment to collect more data about the expert's behavior. You add that data to your giant data set of all the data you've collected so far, and train your next policy, and so on. So you do that for some large number of iterations, and at the end, you could just return the policy that did best at mimicking the expert while you were running it in the environment. So under its own trajectories. So now you might be wondering, how is that related to online learning? Because that doesn't seem apparent at all from this. So that's what I'm going to show you next. And this relation to online learning is what will allow us to provide some good guarantees for this approach. So now I'm going to sort of do a quick introduction to online learning for those of you who might not be familiar with this. And so you can think of online learning as essentially a game between two players. On one side, you have a learner, and on the other side, you have an evil adversary that tries to make the learner look bad. The way this game is played is at each iteration, you have the learner, say, pick a classifier based on its current data, and then the adversary can observe that classifier and pick a test instance where that classifier will be evaluated. And that defines some loss function over a space of classifiers that's being picked by the adversary. And once the learner incurred that loss, then he observes the true label of that instance, and he can update his hypothesis based on that new data for the next round. And so the game just keeps playing on like this. So what we're interested in online learning is minimize this notion of regret, as the other talks talked previously. And this notion of regret is basically just the difference between the sum of the losses that you incur by playing this sequence of classifiers to classify your test instances that are picked by the adversary versus how well you could do if you had known all these test examples in advance and picked the best classifier in your class. So the average regret is just this regret divided by the number of rounds, n. And a no-regret algorithm is basically an algorithm that can guarantee that this goes to 0 as the number of iterations goes to infinity. So how does that relate to Dagger? Well, you can essentially think of each round of online learning, or of Dagger, as a round of online learning. So here, a classifier corresponds to a policy, and you can, if you remember, when we were running Dagger, at each iteration, we're collecting a new small data set of examples by running the current policy. So you can think of these new examples that you collect as the test instances that are picked by the adversary that defines the loss function at that iteration. Sorry. And what Dagger was doing with that new data is it was aggregating it with this aggregate data set of all the data we've collected so far, and then picking the new best policy on that entire data set. So what that corresponds to here is just picking the policy that minimizes the sum of the losses so far. So for those of you familiar with online learning, you'll recognize that this is just a follow the leader type approach. So you can essentially think of Dagger as running this follow the leader online learning algorithm on this particular sequence of loss functions. And what we'll be able to say is if this follow the leader algorithm is essentially no regret, we'll be able to provide some good guarantees for the policy that we learn with Dagger. So in particular, what we can do is relate the performance of the policy learned with Dagger at test time to two quantities that are related to how well we can do on that online learning problem. So one of those quantity is the average regret I was talking about. The other one is how well you can do at classifying that aggregate data set with your class of policies. So what we know is for follow the leader, it's actually a no-regret algorithm for strongly convex loss functions. So if your classification loss includes some type of regularization, it will usually be a strongly convex loss function. And what that means is all these other terms will vanish to zero as you iterate Dagger for long enough. And so you'll be able to guarantee that you'll learn some policy that basically have a number of mistakes at test time that's linear in T and scales with how well you can do at classifying that aggregate data set. And the other important point here that we made with this analysis is that basically these results just follow from the no-regret properties of follow the leader. So what that means is you could run Dagger with any other online learning algorithm to pick the sequence of policies, and as long as it's no regret, we'll be able to guarantee a similar bound like this. So you could imagine like a version of Dagger that does like online gradient descent on the same sequence of loss functions that we've defined, and we'll be able to have the same guarantees. So the key part of the reduction is how we define those loss functions, and as long as we do any kind of no regret algorithm on this, we'll have good performance guarantees. So the bounds I just showed you was for the sort of infinite sample case where you would sample an infinite number of trajectories at each iteration of Dagger. So we can also provide high probability bounds when you just sample a finite number of trajectories. And in particular, if you just sample one trajectory per iteration and run Dagger for order T squared iteration, then you get a similar bound that all with high probability. Okay, so now I want to show you some cool experiments that we did with Dagger. First one is this racing game I showed you at the beginning. So if you remember, what we're trying to learn is some policy that can map these images to the steering you should execute to stay near the center of the road. So I'm going to show you a video of how Dagger did after 20 iterations of training. And basically, each iteration of training was one more lap of training data that we were collecting. That corresponds to about 1,000 time steps each. So it's about like 1,000 training samples that you add to your data set at each iteration. And here all we're learning is a linear mapping from the image features, which were just color values in a resized image, to the steering. So we're basically doing linear regression. And so what you can see is with Dagger, we can perform actually really well at that task. We learn some policy that never falls off the track over an entire lap. But if we compare that to other approaches, what we can see is the both SMILE and the supervised learning approach didn't do that well. So in particular with supervised learning, the performance wasn't even improving as we were collecting more and more data with the experts policy. So last experiment is on Super Mario Bros. So here we're trying to make the computer learn how to play this game by watching a planning algorithm that had full access to the internal game state of the game and could basically beat any stage of the game. And here we're using a simulator from this Mario AI competition in 2009 that could generate random stages. So I'm assuming most of you are familiar with that game, but if you're not, the goal is basically to move the character Mario through the stage by avoiding hitting enemies and falling into holes, and then reach the end of the stage before running out of time. And you can do these 4 actions: jump, right, left, or use the speed button, or any combination of those at the same time. And here the features we were using is just a giant binary vector that describes the objects that were around Mario. And so now I'm going to show you another video of the performance with different approaches. So first here, this is the expert playing. So it's the planning algorithm who's playing the game. And as you can see, it's pretty good, can basically beat any stage of the game. And now this is the supervised learning approach. And what you can see is that it's not doing very well. It gets stuck in the level pretty often, or it also often falls into holes, as you can see there. Now this is the performance with Dagger. Same total number of data over 20 iterations. And you can see it's doing much better. It actually completes an entire stage pretty often, as you can see here. But it's also not perfect, so it still hits enemies quite often. But so if we compare the average distance traveled by Mario over like this random distribution of stages that we can generate, what we can see is that Dagger does much better than all the other approaches. So here, 3,000 corresponds to about 70% of a stage on average that's being completed. And so we compared here with SMILE, CERN, and also supervised learning. And each algorithm was run for 20 iterations, so we're collecting 5,000 training samples per iteration. So in conclusion, well, the sort of take-home message of this talk is you can do these simple iterative procedures to obtain much better performance, practice, and theory on these kind of non-IID supervised learning problem, like imitation learning. Something I didn't have time to talk about is that you can actually apply this to do structured prediction. So one way you can do this is by doing an approach that's similar to CERN, where you transform your structured prediction problem into like a sequential prediction problem. That's sort of a degenerate form of imitation learning. And then you can apply Dagger to learn a classifier that can essentially construct the structured output by making this sequence of predictions. And so we have actually a structured prediction application in the paper on handwriting recognition. And we also have a new paper coming up in a computer vision conference doing scene labeling applications. So I'll just stop here. Thank you very much.